All right, so here is an example of a two-way ANOVA. This is the example that our Barry Cohen's textbook presents in chapter 14. So I wanted to walk through the example to help facilitate understanding, even though I know you guys have all read it. So the example in the textbook talks about an experiment that was a factorial experiment. So that means when we say factorial experiment, we have two factors and we have all combinations of those two factors. They're fully crossed, or all possible combinations exist in this experiment. So to understand the experiment, we have to first figure out what's the dependent variable. And for an ANOVA, the dependent variable, or DV, has to be a continuous measure. Hopefully normally distributed, homogeneity variance, all that good stuff. So in this example, we are comparing video game scores that simulated driving a large truck at night, like a semi-truck. So they're looking at like cognitive function and awareness and reflexes, so complex motor tasks. So there was a score that the participants would get on this driving game that had a range, so it's a dependent variable that's continuous. Now, the participants, they had two different ways of categorizing the participants, and they were randomly assigned. The first factor was their sleep deprivation. Yeah. How would you like to do this? They spent 4 days in a sleep lab. So the first factor, the first independent variable, and again for ANOVA, even though the dependent variable has to be a continuous score, the predictor or the independent variables have to be categorical. So they have to have categories. So the first categorical variable that's an independent variable is sleep deprivation. So factor A, or the first factor, was sleep deprivation, and it had 4 levels. So there are 4 possible sleep conditions that each participant was randomly assigned to. First was controlled. For all 4 days, they got to sleep whatever their normal schedule was. Group number 2 were the jet lag group, and they could keep getting the regular amount of sleep they got, but they were not allowed to sleep between 11 p.m. and 7 a.m. So jet lag sleep. The third group is the interrupted sleep, and they were allowed to get as much sleep, or the regular amount of sleep, but they could only sleep for 2 hours at a time, and after that they'd have to be awake for at least 1 hour before they could go back to sleep. And the fourth group, oh, don't you wish you were in this experiment and you were assigned to 4 days of total sleep deprivation, where they completely had no sleep whatsoever, or at least, as I'm assuming, as much as they could. So the participants were randomly assigned to one of these 4 sleep categories. And if that was the end of it, we could do a one-way ANOVA, like we learned in chapter 12 and in chapter 13 when we looked at post hoc, pairwise, and contrast statements to compare the groups. But in this experiment, it was a factorial. So they had one factor that was these 4 sleep conditions, but they also had a second factor they wanted to investigate, and that was if the video game score, or their cognitive function, their complex motor function, was affected not just by sleep, but also by possibly a stimulant. And for stimulant, there are 3 levels. One was a placebo, a control group. They were given sugar pills, even though they were told they were caffeine pills. Group 2, they actually did get caffeine pills, and they were told it was caffeine, so they could compare placebo effect versus actual caffeine effect. And then the third group, oh, can't you imagine if you were in the total sleep deprivation in this third stimulant group? Oh boy. This third stimulant group, they were given electric shocks when they made mistakes on this video game, and then they got paid money if they performed well. So this is the scenario for this factorial or two-way ANOVA. And so we can call it a two-way ANOVA because there are 2 factors, 2 categorical independent variables. The first being the sleep situation, and the second being the stimulant. 2 ways of defining or assigning the participants. There's 2 different categorizations. And we have 4 levels of sleep, 3 is stimulant. So we can say it's a 3x4 or a 4x3. So when you do a two-way ANOVA, there's no reason why you would choose one variable to be the rows and the other to be the category, one to be the A versus the B. We're just going to go with the way the book did it in this case. So we've got 4 sleep deprivation categories. So it's a 4-level independent variable and 3 stimulant factor levels. And so together, 3x4, there's a possibility of 12 combinations, 4 times 3, 3 times 4. So in each of these 12 combinations, they randomly assigned 5 participants for a total of 60 participants. So our overall sample size, or N with a little n with a T, or a capital N for a total sample size, is 60. But then each of those cells, each of those combinations had only 5 participants each. So a little n would then be 5. How many people for each combination? It's important to note that these categories are mutually exclusive. Each subject only had 1 sleep deprivation and 1 stimulant. They were mutually exclusive. So if someone was in the jet lag caffeine, they couldn't be in the jet lag reward. Or if they were in the control placebo, they couldn't be in the total deprivation placebo group. They only could be in one of the combination groups. So here's the data that was presented in the textbook. So in each one of these green cells, we have the scores on the video game for driving that truck for the 5 people that were in that scenario. So if we look in the upper left-hand corner, the control placebo group, which you would think maybe would be the best because they're not getting caffeine, they're not getting shocks, they're not getting payments, they're not getting their sleep messed with. Their scores were 24, 20, 29, 20, and 28. So that was their scores. And you can, if you scan down here, you look like, I think the lowest score was 10. So they're all double digits, 10 till about 28-ish were the scores on this driving test. So I've shown my code here in R for how to enter the data and get this in long format, which when you do that, it'll look like this. We'll have 1 line per person. So we'd have 60 lines of data, 60 observations in this data set, 1 observation per person, 1 score in the video game. We only have their score after the 4th day of having this go on. But we've got 3 variables or 3 columns in our data set. The first being which sleep group they were assigned, the second being which stimulant group they were assigned, and then the third column being their score. So sleep and stimulant, those are our 2 categorical independent variables, and then the score is our dependent outcome continuous score. And now we want to ask the question, does sleep or stimulant or some combination produce better or worse results on this video game? So the first thing we're going to do is we're going to take this data table, and this is the full data table because there's only 5 per group. There's still 60 numbers to look at here, and if you try to eyeball it, it's hard to kind of get an idea of what any patterns are. So we're going to collapse this down to what we call a means table. And a means table would still have the same arrangement here where we have 4 rows, 1 for each sleep condition, and 3 columns, 1 for each of the stimulant conditions. But instead of having all 5 scores in each cell or each combination, I'm going to do the average. So that's the means. If I wanted to do this in R, I could take my data set, group it by sleep, and ask for table 1 from furniture package, and it would give me the average and the standard deviation and the sample size for each of the 4 sleep conditions. Now we said there were 5 participants assigned to each combination. So if we're looking at the own schedule sleep, there were 5 on the placebo, 5 in the caffeine, and 5 in the reward. So here we're collapsing all the controls, no matter what stimulant they're on. And we can do the same thing. Instead of collapsing across row, we can collapse down the columns. And so the syntax looks almost the same. We're starting with our data set, we're piping it into a group by, and we're asking for the descriptive table 1 on the score. The difference are we going to collapse or group by sleep or by stimulant. And then this third in the green outline, this third little chunk of code, I've done something a little bit different. Instead of grouping by just sleep or just stimulant, I'm grouping by both. I'm summarizing to get a mean score, and I'm spreading that out so that I can get a table that has all those green center cells, their averages. So let's look at this green marginal means table that's on the slide for a second. I'm going to add first the sleep condition averages. So these are the sleep margins. The sleep margins, I've labeled them blue, so it's collapsing across a row. There's 15 people in each sleep condition. And then in pink, I've collapsed down the columns. So across each stimulant, now we've got 4 green blocks stacked up in a column. So 5, 5, 5, and 5. Now we've got 20. So in this experiment, we would consider this a balanced design because each cell, each combination condition between sleep and stimulant has the same number. They all have 5 people. But if we look at the column sample sizes, the marginal column sample sizes, those are 20. If we look at the row sample sizes, the row margins all have 15. So it is balanced because all the rows have the same number and all the columns have the same number. But I just wanted to point out, because this makes a difference in your homework and some situations you're going to find yourself in, hopefully in real life, or unhopefully, that the column totals and the row totals for sample sizes are different than each other. And that's because in this situation, we have 4 rows and 3 columns. Now we have to have 60 total subjects. So that's why that's that way. So now I put in blue and pink the margins. The margins are collapsing across rows and collapsing across column. Then down in the very bottom lower right-hand corner in gray, I have the grand mean averages. So you'll see the capital N, the sample size, is 60. That's the overall sample size. And then the overall average on this video game was 21.2-ish. Now I'm going to take and so that's the blue and the pink numbers that are over here on my screen that I've put on the margins on the outside. Now I'm going to take that green data and I'm going to take those cells of 5 people and average them out. I already asked R to give me the numbers. So now I've replaced all of my blocks, all my cells in my table with just averages. This is now a means table. In all of the cells of the table, it has just averages, just means. This makes it a little easier if you're trying to make comparisons and try to eyeball any kind of patterns or trends that you might see. Again, the more numbers you have, the harder it is for your eye and your brain to make sense. If you can plot these, it makes it a lot easier to kind of get a feel for what's going on. And I always stress, you want to understand your variables 1 at a time and 2 at a time, maybe even 3 at a time before you ever try to make a more complicated model. Because if you can't understand your variables 1 and 2 at a time, if you try to throw a bunch of stuff into a kitchen sink model, you're not going to be able to interpret the results you get out. So here I've kept our little means table, but I'm going to go ahead and plot it. Now there are multiple ways to plot a means table like this. Now this is a 2-way table because we have rows and columns. We have 2 grouping variables. So the blue row margins, we can do a row-wise plot. Then the pink column margins, we could do a column-wise plot. And then in the green cells, we could do what we would call an interaction plot, where we have all combinations of rows and columns, all combinations of sleep and stimulant. So those are the 3 main ones. So when you have a 2-way ANOVA, a 2-way factorial design, where you have 2 grouping variables, you end up with 3 effects. You've got sleep, you got stimulant, and then you have their interaction. And this is the benefit of doing a 2-way ANOVA instead of just 2 one-way ANOVAs, because we can investigate the effect of sleep, the effect of stimulant, and see if one moderates the other, if there's an interaction, if the effect of one of these things depends on the other. Does the effect of the stimulant depend on the sleep that they're getting? Or does the effect of sleep depend on whether or not they're on the caffeine pill? So that's the idea of an interaction. So first, let's take those row collapse row margins that I have in blue, and let's plot them. 25.6, 24.47, 18.7, 16.73. There's only 4 numbers here. And it looks like as we're going down our rows, the scores on average are going lower. So the less sleep, the more that they're messing with someone's sleep, the more worse they're doing on this video game. And here's how we would write the code. Now this will give us not just the means, but also little error bars that are plus or minus the standard error for the mean. So I've taken my data set, piped it into ggplot, and on the x-axis, I'm going to have that category of sleep, our independent variable, just one of them, of sleep. And then on the y-axis, I'm going to have that continuous score, our dependent variable. And then the stat_summary command will give us a dot for each of those 4 means, and then little bars for the standard error, the mean. And we can visualize here, yes, as we go from own sleep to jet lag to interrupted to total lag, we see the scores going down. And the nice thing about this plot is we see the averages are going down, but we can see with the margin of error on that standard error for the mean, this does make it look like, even eyeballing it, that this is probably a statistically significant effect, because even with those error bars, there is some separation. Now, own sleep and jet lag, there's quite a bit of overlap there. Those two might not be statistically significantly different from each other, but there's a definite separation when we move from jet lag down to interrupted, and then even further down to total lag. So this helps us understand the connection between sleep and the video game score, 2 variables at a time. So this would be a marginal means plot for the effect of sleep. Here, that's the row factor. We do the same exact code, but swap out the x equals variable. Instead of the categories of sleep, let's do the 3 categories of stimulant to get the main effect of stimulant. So these 2 plots, they're looking at one of the independent variables, one of the factors, and compared to the outcome variable, our dependent variable that's on a continuous scale. And these, when we're only looking at one of our factors at a time, these are called main effects plots. So the one in blue for the rows of sleep, eyeball says, yeah, we got something going on there. More messing with the sleep equals lower score. If we look at the pink outlined plot, I have the 3 margins for stimulant. Now if I look at the first one, is sugar pill, and then the middle one is caffeine. Oh, that looks like it's higher. It looks, the eyeball method is telling me that caffeine is helping them do better on this driving test. And then that third group, the electric shock / cash payments, looks like it's somewhere in between. Now, it's important not to take this too seriously at this point, because this is just a visualization and it isn't a p-value. It isn't a statistical test. And especially in this scenario, we only have 5 per cell. So we have pretty low power with small sample cells. Even though our overall sample size is 60, we've got quite a bit of standard error going on here. The second thing is this blue plot is looking at sleep collapsing across stimulant, ignoring stimulant, collapsing across it. The pink plot is looking at the effect of stimulant collapsing across sleep. What might be hidden in these 2 plots is the interplay, the interaction between sleep and stimulant. And to get that, you've got to make another plot that has not just one or the other, but both of the independent variables. We need sleep and stimulant both. Now, there's at least 3 or 4 ways I can come up with to plot this, because we only can have one variable on the x-axis and one variable on the y-axis. And with an ANOVA, you always want to put your dependent variable, your continuous outcome variable, as the y-axis. And then you have to choose one of your 2 factors for the x-axis. You could choose sleep or stimulant, but you only can put one of those on the x-axis. You're going to have to do something else with that second factor, that second independent variable. One thing is to color by the other factor. Another is to connect with different line types. Another option is to do different panels. I'm going to show you here doing with color, using color to do the second factor, so we can look at both factors simultaneously. There's pros and cons of using color. It's really visual if you're not colorblind, and you're not going to have to worry about printing in a black and white journal, or photocopying, or black and white printers. Another way to get around the color is to use different shapes instead of all circle dots, and to different line types, different shades of gray if they're larger. Well, let's go ahead and show you this one. So in green, I'm using green to outline this plot for the interaction because I'm looking at both of the factors at the same time. So here I haven't connected the dots, but I will be showing you that on the homework. And hopefully we'll go over that in the office hours tomorrow. But if we look at the green dots, those are the dots. Well, I'm showing them with triangles. Oh, how nice of me. I use triangles so you colorblind people, you can see. The green triangles here are for the stimulant or the caffeine stimulant. And we can see that for the first two green triangles, moving from left to right, for own sleep and jet lag, those caffeine scores are right in the middle. But if we move to the interrupted and total lack of sleep, it looks like the caffeine groups are doing much better than the sugar pill and the electric shock. Both of those two groups, those pinkish coral circles and the blue squares, are both lower, although those two are really close together. This plot is an interaction plot. Now, this one is just from the summary data visualization. It's not based on the model. We haven't done any modeling yet. It's just summarizing the data. But if we look at these green dots or green triangles compared to the blue squares and the red circles, if we connected the dots, we'd get very different lines. Now, they're not ever going to be perfectly straight in real life, especially with more than two. If you have two, they'll be straight. But here we've got 4 points to connect. But if we connected the dots for the green triangles versus the blue squares, we would get lines that were crossing. Now, that's kind of the classic idea of an interaction, lines that are crossing. But the more full version of the definition for interaction would be if you connected the dots and the lines are not parallel. Now I'm going to put in the caveat here. They are not ever going to be perfectly parallel. And so even if they cross, what we want to know is, are they statistically significantly different in slope, or are they close enough we could treat them as if they're parallel? Sound familiar? Close enough? That's what statistics is about. Okay. So we want to go ahead and do our statistically significant tests for the effect of sleep, the effect of stimulant, and the interaction between the two. Does the stimulant moderate the effect of sleep? Does sleep moderate the effect of stimulant? The math doesn't care which one's moderating the other, because in an interaction, it's a two-way interplay between the two factors. So here I've drawn and colored in what I like to call a degrees of freedom tree. And we're going to start at the top and we're going to work our way down. Now, the rules about the degrees of freedom tree is when we have a number and when we break it down into 2 smaller numbers, we can't lose anything, we can't gain anything. It's like matter can't be created or destroyed. So same thing with degrees of freedom. And I'm using the same color scheme I've been using throughout this whole slideshow. So C is the number of columns. Now, if you think back to our means table, columns were our stimulant. We had 3 stimulants: the placebo sugar pill, the caffeine, and the electric shock / cash payments. So little c in this case is 3. We have 3 columns, 3 stimulant levels. In blue, our rows were our sleep conditions. There were the 4 sleep conditions. So R in this scenario is 4. And then little n is the number of subjects per cell. In this case, it was 5. We had 3 by 4, 12 combinations, 5 per cell, for a grand total sample size of 60. And I think it's important to note this is balanced. So all of those cells had the same number, n, 5. In real life, you're often, even if you plan to have balanced cells, something's going to go wrong with someone and you're going to end up with some kind of missing data or some complication, and they're probably not going to be perfectly balanced. ANOVA methods demand balance in your cells, but they can tolerate a little bit of imbalance. A little bit is key. If we have cells or combinations that have more or less participants than other cells or other combinations, then you need to do some work to make the ANOVA be reliable, or you have to move to a different method. And that's my preference, is to go to a different method. And those other methods would be regression or multi-level regression, mixed effects models, multi-level models, whatever you're going to call them. Those are courses that I teach, and I highly, highly suggest them. But today we're just going to stick with the ANOVA. We're just going to, in this recording, just do this basic example, nice balanced cells. So here's our degree of freedom tree. Now the formulas for this are in the book, and they're also on the formula sheet that I put together for our course. So we're going to start at the top. The degrees of freedom, the total degrees of freedom, is the total sample size minus 1. R times N times C, rows times columns times number of participants per cell. So 60 minus 1 is 59. That's our total degrees of freedom. Now, the degrees of freedom branching tree is a mirror. It's perfect, same branching that we have with the sum of squares. So we can think in terms of sum of squares too. So the sum of squares, we're going to partition our variance, partition our variation into different piles. In a one-way ANOVA, we partition into between groups and within groups, explained and unexplained. And that's the first step we do in the two-way ANOVA. So we're going to take our total degrees of freedom, 59, and we're going to split it into between cells and within cells. Between cells, degrees of freedom is the total number of cells minus 1. Number of cells is rows times columns. Number of rows times number of columns minus 1. 4 rows, 3 columns, that's 12 cells, minus 1 is 11. Our between cells degrees of freedom is 11. So if we start with 59 at the top and we branch to 11, then what's that white box got to be? We got to add up to 59. 11 plus what is going to give us 59? 48. I can subtract to get that number, but there's also a formula. The within cells degree of freedom is the total sample size minus RC. It will give you 48. So that white box here, the within cells degrees of freedom, that's going to be our denominator degrees of freedom for all 3 of our F tests. 3 F tests, but we only have 2 factors, sleep and stimulant. Oh yes, we have sleep, we have stimulant, but remember we also have their interaction. So even though there's 2 independent variables, we actually have 3 effects that we're testing. 2 main effects and the interaction between the factors. So that's the last branching on this degrees of freedom tree. So our gray between cells degrees of freedom of 11, we've got to break it up into 3 piles. And we do the same thing with the sum of squareds. We're going to do our between cells sum of squared and break it into variation due to row variable, variation due to column variable, and variation due to the interaction. So on the blue box, the rows. How many rows did we have? That was our sleep conditions, 4. The degrees of freedom for rows is 1 less. So the degrees of freedom for the row variable is 3. Now in pink, columns. We had 3 columns, 3 different stimulants. So the degrees of freedom is 1 less, 2 degrees of freedom. The interaction, well, let's see. We've got 11 degrees of freedom between cells, and we've already broken it into the blue 3 and the pink 2. We've got 3 and 2. What else needs to go in the green box to have it all add up to the 11 that it branches from? Branching into 3 piles here. 6. That's the magic, the number here. And you can also use the formula number of rows minus 1, number of columns minus 1, and multiply those 2 numbers. We had a 4 by 3. Subtract 1 from each of those. 3 times 2 gives you 6 for the interaction degrees of freedom. So here I've circled in purple rows, columns, and their interactions. That's sleep, stimulant, and then moderation, or the interaction between the 2. Sleep and stimulant. Those are going to be the 3 numerator degrees of freedom, and their partner sum of squareds are going to be have mean sum of squareds that are going to go on the top of our F ratios. Our error, our residual, our within cell variation is going to be the denominator. So for the rows, for the sleep condition, our degrees of freedom are going to be 3 and 48. Remember, F tests have to have 2 degrees of freedom. In pink, for the columns, for the stimulant F test is going to have 2, 48 degrees of freedom. And the interaction between sleep and stimulant is going to have 6,48 degrees of freedom. So in this example, since we had 4 and 3 for our rows and columns, first factor, second factor, number of levels, those are not the same number. And when we do the interaction, we get 6. That's another number. In this case, we're going to have 3 different degree of freedoms. And we're going to have 3 different critical values when we look up the significance for main effect of sleep, main effect of stimulant, and the main effect or the interaction between the two. Okay. So here is the code to actually do the Twoway ANOVA in R using the AFEX package, and it should look kind of familiar. Like always, we're going to, I'm saving this to a name, ANOVA Twoway, and I'm going to start with my data set, piping it in. We're using the same package and command we used for one-way ANOVA. This is why I teach this one, because we can use the same command, AFEX :AOV_4 for all the types of ANOVAs we're going to learn. And then we're going to have the formula. Same way for all the types of ANOVAs we're going to do. First, you name the continuous dependent variable. Here, we're just calling it score, the score on that driving test. Then tilde wave, what are we going to predict it with? Now, this is a little bit different. Before, we would have put just the grouping variable name. But in this case, we have 2 grouping variable names. We have sleep and stimulant. And to include them both with their interaction, you put an asterisk, that little star, Shift 8 key on your keyboard, in between the names of both of those variables, sleep, asterisk, stimulant. This will do the main effect of sleep, the main effect of stimulant, and the interaction between sleep and stimulant. Now, those variable names, sleep, stimulant, and their interaction, are right after the tilde wave. And then we have the plus, and then in parentheses, 1 vertical bar ID. The 1 tells us that we have 1 observation per person. You could think of them, they might have really done this and taken 4 different scores on 4 different days. That would be a repeated measures design, and we are going to learn about that next week after we take this exam. So hold on to that idea to come. But in this case, we only have 1 observation per person. So the full formula is score, the dependent variable, tilde wave being predicted by sleep, stimulant, and their interaction. So we're using the asterisk between those 2 variable names. Plus, we only have 1 observation per person, per ID. In that vertical bar, you can read it as per. And then comma, data equals dot to pipe it from above. And that's all you have to do to run the ANOVA. Now I've stored the ANOVA as a name, AOV_Twoway, so that I can extract some information from it, possibly do some plots and some post hoc tests if needed. So the easiest way to get the table of information out of the model is to do the name that you saved it as, $, capital A, NOVA, ANOVA. And this is what the output will look like. Now remember, just like in one way, that first line that says intercept, we're ignoring completely. Now let's see if some of these numbers look familiar. Let's look at the degrees of freedom part first. Sleep, how many sleep conditions did we have? There was 4 levels, so that makes 3 degrees of freedom. Stimulant, how many stimulants were there? Placebo, caffeine, shock money, 3, so that's 2 degrees of freedom. And sleep by stimulant interaction, 6. Oh, that's really great. And then down here in R, it'll say residual. Residual, error, within cell, those all mean the same things. You'll see all of those 3 used interchangeably for different software and different, just different lingo, means the same thing. One thing I want to point out, in our formula, we use the asterisk between the sleep and stimulant variable names, but in our table between sleep and stimulant, we see a single colon. So in R knows we like to be lazy. The single colon is really the way we state an interaction. But if you put an asterisk instead, then it's a shortcut for saying, I want both of the main effects and the interaction. So that's what our table looks like. Now here I put a full fancy ANOVA table, and this will match the ANOVA table that it layout that is presented by say SPSS, data, a lot of software packages. It's the same numbers, although some may or may not show up on every software, but this is the full ANOVA table. Difference here, this one has a top line for between cells. The between cell is just adding up all of our effects, sleep, stimulant, and the interaction. If you add those all up, like for the first two columns, 3, 2, 6, that adds up to 11. It's just a combination line. It's not going to help you know anything anymore. Here in the white cell, this is the MS, the mean sum of squareds for the residual. MS residual, MS within, MS error, those all mean the same thing. Often it'll be called MSE. And even though a lot of software outputs it, that usually is not something that you need to report when you're writing up an APA. It never hurts to throw it in there, but it's usually not that useful of a number. Here, the mean squared error is 16.39. That tells us the overall variance in these scores after accounting for sleep, stimulant, and the interaction is 16, which if we square root it, we get about 4. So the standard deviation of scores is about 4. Usually descriptive statistics for standard deviations, standard errors are preferred, but there it is. So usually when we run an analysis, the first part of the output we look at, get really excited, is we look at the p-values. P-values tell us statistical significance. Now for a two-way ANOVA, or any model that has an interaction of any kind, you always want to focus on, interpret, and figure out the highest level interaction first. Now in this example, we have 2 independent variables, so the highest interaction is a two-way interaction, the interaction between sleep and stimulant. So when we look at this output, we want to look at the sleep by stimulant interactions p-value first. It's a little, the way every software I've ever seen always puts the main effects first and then the interactions. So you actually have to scan down to the bottom of the table first. So you can look at it in this colorful table that I built or in the R output, either way. Our p-value for the interaction in this case is 0.087. What does that tell us about the interaction? It's not statistically significant in this case. The picture looked very statistically significant, but the catch there is our cell sample size is only 5. And so I think we're underpowered to make that declaration of statistical significance, even though the effect looked like it was moderate in effect size. So So in this case, the interaction is not statistically significant. But if it was, that is what we need to focus on, and we need to interpret, and we need to write about first and foremost. If there is a statistically significant interaction, that is where the focus needs to be, not on the main effects. Because if we have an interaction, that is telling us the effect of sleep depends on which stimulant they were receiving. Or we can flip it around. The effect of each of the stimulants depends on how much sleep they were getting. And if there is that interaction, if there is the interplay, then it usually does not make sense to collapse across one and ignore one of the factors in order to interpret the other factor. So main effects should only be interpreted if the interaction is not significant. That's a pretty strong blanket rule that we should follow. So in this case, the interaction is not significant, so we could go on and look at those main effects. So we're just going to move ahead as if that interaction was significant. That 0.087 had been a little bit smaller. And I want to show you how to do an interaction contrast statement. So we did linear contrast statements when we did our one-way ANOVA in chapter 13. And now that we have a two-way ANOVA with an interaction built into it, we can do another kind of contrast statement. And these are some of the more maybe a little bit hard to understand the first 1, 2, or even 3 times through. So here's the, I'll try to slow it down. and help make this hopefully make a little more sense than when you read the book. So for an interaction contrast, the whole idea of an interaction is that we have interplay. And a contrast statement, we want to simplify it down. Now, when we did our linear contrast, we talked about a teeter-totter, and even if we had 4 groups or 3 groups, we want to lump them together on 2 sides to make a pair of groups. And we want to do something similar. We want to get down to a pair, but not just a pair, but 2 pairs of the most extreme. So for this one, I'm going to focus on caffeine and placebo. So those are my pair for my stimulant, caffeine and placebo. And I'm going to look at sleep, the pair, no sleep versus normal sleep. So I brought back our means table, and I am going to gray out everything else but just these 2 pairs. So I'm going to leave highlighted, leaving green, the 4 cells for caffeine and placebo, those 2 columns, and no sleep and normal sleep, those 2 rows. And the combination of the 2 columns and the 2 rows will give us 4 cells. So this, again, we would only do this if the interaction was significant. Didn't quite reach it in this case, but we're moving forward, full speed ahead. So often, if we're doing a contrast statement, you would pick the pair of levels in each of these factors, so the pair of stimulants and the pair of sleep, that were the most extremely different from each other, or that you had the research question or hypothesis that was focused on the most. So you're going to take those 4 cells, those 2 pairs, and now they have to be 2 rows and 2 columns in grid fashion, and you're going to focus on those. So again, one of my fancy slides, here we go. I'm going to pull them out and pretend like we don't have the rest of the data for a moment. Now, when I pulled them out, I pulled out the means. So now we have a grid, a small 2x2 grid with 4 means, 24.2, 25.0, 14.2, and 21.4. And what we want to say with these interaction contrasts is not just, is there a difference, but is there a difference in the differences? It's a double negative. Is there a difference in the differences? Does caffeine effect in normal sleep, is that the same as caffeine's effect in no sleep? We've got to involve both sleep and stimulant at the same time. Let me say that again. In the purple box, caffeine's effect in normal sleep. And then in the green box, the light green, caffeine's effect in no or total lack of sleep. Now, we've got a double negative, a double subtract, so we're subtracting a negative. Now, I put some parentheses here. In the purple, we have the cell 1, 1 and the cell 1, 2. Their averages subtracted. And then in the green total deprivation box, I have the cell 2, 1 and the cell 2, 2. Now, those numbers are based on this extracted 2x2 grid here. But we've got a subtracting in each parentheses and a subtracting between the parentheses. And if we go back to algebra, which I've been working on, thank you coronavirus, with my children in 9th and 7th grade, subtracting a negative, double negative makes a positive. So I've distributed the subtracting through the second set of parentheses to get rid of the parentheses. Now, I'm using a capital L here. The capital L we use to denote the linear contrast, and we no longer have a linear contrast. We have an interaction contrast here, but we're still going to use the capital L value that we learned in the linear contrast. So we've got 4 means, and we've got the first one, subtract the second one, subtract the third one, plus the fourth one. Minus, minus, plus. And that comes from the double negative. We could think about, if we were just doing a sum, adding it all up, having coefficients or linear coefficient weights of 1, -1, -1, 1. I brought them out and made them bold red letters. So these are our C weights. Remember from the linear contrast, our contrast weights. In the red again are 1, -1, -1, +1. And the way we did the work before, we had to pick the weights. And what were the rules about the weights? Yeah, it made some positive and some negative so that they would add up to 0. 1, -1, -1, +1. Yep, they add up to 0 because we got positive and negatives. And we want the teacher taught her to balance. All ones, it's going to balance. So our L, that's how we specify our contrast C weights. And then we've specified how we're going to calculate it's not a linear, it's an interaction contrast value L. And then to finish this up, we're going to have to do the sum of the contrast weights squared. So they're all ones, positive or negative. So if we square them, they're all going to be positive ones. Add them up, it'll be 4. So that's this other kind of tealy box here. Now we're going to take, go back, let's look at that fancy animation of my slide. We're going to take our 4 values and we're going to plug them in place of our X bar values. 1, -1, -1, 1. The difference between placebo and caffeine in the normal sleep group, those averages are 24.2 and 25. If we had normal sleep, the caffeine and placebo averages are almost the same thing. There's a very, very little difference of 0.8. But in the total sleep deprivation, the no sleep group, the averages with placebo were 14.2 versus caffeine was 21.4. That's a bigger difference than the 0.8. So again, we're looking at differences and differences, double negative. So if we weight those averages, the green average numbers, by our red contrast weights and add it all up, we'll get a number 6.4. 6.4 is our contrast value. And the sum of squared for that contrast is given by this other formula. Now, these formulas that are in these teal boxes, the sum of the contrast weight squared and the sum of squared for the contrast, these are the same formulas that we had back in chapter 13 when we were doing linear contrasts. The only thing here is we're doing interaction contrast, but same mathematics apply. So little n is our common sample cell size, that's 5. L, capital L, is the one we just calculated up here, 6.4. And then the sum of the CI squared, that's the sum of our contrast weight squared, that came out to be 4. Plug our numbers in and chug it out. We get a sum of squared for our contrast of 51.2. Aren't we glad that we get to do this with software from now on? And then the F value for the contrast would be to take that sum of squared and divide by the mean squared within. Now this mean squared within that we're going to divide by is the mean squared within, or the mean squared error, or the mean squared residual, whichever name we're going to give it, back from our ANOVA table for our overall ANOVA model, which was 16.39. So here we get the F for our contrast, our interaction contrast, is 3.12. Is it statistically significant? For an F value, we would usually look up the degrees of freedom in the table, the F table. Is that A11 or A7? I get them backwards. And that would be what we would do to find out if we had a statistically significant interaction for this contrast, this pair of pairs, if this was pre-planned. Now, if it's pre-planned, you can look up the p-value hunky-dory. If instead of being a priori / pre-planned, if instead this was a post hoc, generated, we decided to do this after we'd gathered the data, after we'd ran the ANOVA, after we peeked at our data, then we needed to do a correction for multiple comparisons, a post hoc correction. And to do this, we are going to use Chaffee's test. Chaffee's test is the best one to use to correct for multiple comparisons or the fact that we have a post hoc comparison for an interaction contrast after a two-way ANOVA. Now this interaction contrast, because we did a pair of pairs, it's a 2x2. And so the degrees of freedom for this contrast, again, we did number of rows -1, number of columns -1. They're both 2 rows, 2 columns, subtract 1 from each, multiply, it's a 1 degree of freedom for the contrast. So the F test would have 1 for the numerator degrees of freedom. The denominator degrees of freedom is going to be the same denominator degrees of freedom from the overall and F test. So we could do that, and that would be fine to look up the F critical value and the P value if we'd pre-planned it. But if not, we're going to do Chaffee's test. Chaffee says to take those interaction degrees of freedom, so that's 1 in 48, and look up the F value, but we're going to times it by a number, the degrees of freedom for the interaction. The interaction here would be the interaction, this is the interaction for the 4 by 3, 6 degrees of freedom. And so Chaffee's cutoff, Chaffee's critical value is 14 and change. Well, our test only gave us a value of 3. If our F statistic for our F test was only 3, but Chaffee's critical value said we needed to get past 14.4, not statistically significant. So this mirrors our interaction omnibus F test that said our p-value was 0.08. It was bigger than 0.05. So our ANOVA said we had no significant interaction. And even though we disregarded that, went forward, our contrast, our interaction contrast, is also saying no interaction. Now, I said before, an interaction is apparent in your means plot by having lines that are crossing or at least not parallel. Now, if we go back to our pairs, normal and none sleep, total lack of sleep, and placebo and caffeine, these 4 purple squares now, I've highlighted them on the plot. So let's look at the first pair. In our own scheduled sleep, taking caffeine or placebo, those 2 cells had almost the same average on the driving test. There we're only different by 0.08. Those points on our means plot, were very close together. So caffeine has very minimal effect if you're getting regular sleep, at least on this driving test, for this possibly fake data. But in the total lack of sleep situation, that factor level, the caffeine takers scored higher, quite a bit higher, 7.2 points higher on average than the placebo group. If we connect the dots here with these purple lines, are they parallel? I'm hoping you're saying no, they're not parallel. There is a difference in the differences. Our first 2 points are only different by 0.8, and our second pair is much wider of a gap, 7.2. So our gap is wider at one side than the other. So when we connect the dots, we get lines that diverge or become wider apart. This is not parallel. But because the F for our contrast was much smaller than the F for Chaffee's, we have to say that there's no evidence of an interaction. Even though the plot looks like these lines are not parallel, we have to conclude that they're they're close enough to parallel to be considered parallel. So even though the averages made it look like there was an interaction or an effect, that caffeine's effect depended on how much sleep you had, there is no statistically significant evidence that caffeine has a different effect in normal sleep versus total deprivation. And again, the reason for this is probably lack of power in this sample. We only have 5 people per combination. This is why it's important to do a power analysis before you gather data, because you wouldn't want to go to all this trouble to find out, yeah, there's an effect, but we can't say so with a surety by test. So, word to the wise, do a power analysis. And that's the end of our example slideshow. I will wrap this up, get it uploading on YouTube, and hopefully this will help. We'll see you soon.